talk that I would like to state today devoted to extensive uniqueness and LP regularity properties of Cauchy problem for non-local Schrödinger equation. I would like to remember that the existence and the regularity properties of solution of Cauchy problem for Schrödinger equations studied in let I will show these mathematicians that really have a deep result in the field of theory of Schrödinger equation and Schrödinger semi-group. First of all, for the stationary Schrödinger equation, it is spectral properties and the properties of Schrödinger semi-group. I can show the well-known mathematics by Simon and the students really for the stationary Schrödinger equation. But for the time-dependent Schrödinger equation, I would like to result of Thierry Cazeneuve, the French mathematics, well-known mathematics, that have a different results to devoted the L2 theory of the existence, uniqueness, and the regularity properties of linear and nonlinear Schrödinger equation. Moreover, in this field, the remarkable result well-known mathematician Tosya really gave his contribution in the L2 theory of the Schrödinger equation. So, just Weinstein, dispersion small amplitude solution of the Cauchy equation, and have at the same time the Schrödinger equation. But one of classical result, Gimber and Beller, symmetric properties of related estimate for the dispersion evolution equation, mainly for Schrödinger equation. Moreover, one of fundamental results, devoid well-known mathematics, Jean-Borg-Bourguet, global well-posness of focusing and the defocusing critical nonlinear Schrödinger equation. Then what Kiel and Teres Tau, also the well-known mathematician, have a structured type estimate for the Schrödinger equation. For the abstract differential equation, what I can show, for example, Okazawa, Suzuki, Yakota. So tam Allah bilen Ashur Aliyev really have a little result for stability of the Schrödinger and the difference method for solution, numerical solution of the Schrödinger equation. Now, what I think I have no great time. So first of all, I would like to continue that the most of above result consider the classical Cauchy problem for Schrödinger equation, classical equation. That have been considered if has some symmetric property and is also the gradient of some function f. Thus, at least formally, it have both conservation charge and the conservation of energy, that is, satisfies this classical equality. Clearly, the charge and the energy involved in L2 and the H1 norm stability, L2 stability spaces, when solution belong to these spaces. Therefore, it is appropriate to solve the local Cauchy problem in the space of L2 and the H1 Rn. Indeed, when it is possible to solve the local Cauchy problem in L2R, then global existence follows immediately from the conservation of charge. And when it is possible to solve local Cauchy problem in that belong to H1 spaces, then the global existence follows from the conservation law if satisfies nonlinear operator satisfies some certain growth condition. In this talk, the Cauchy problem for linear and the nonlinear non-local Schrödinger equation are studied. The equation involves the abstract operator with general kernel operator function, whose Fourier transform are operator function defined in Banach spaces E that we will define each of Banach spaces together with some growth condition. By assuming enough smoothness on the initial data and the operator function, the local and the global existence, the uniqueness of solution are established. We can obtain different classes of non-local Schrödinger equation by choosing the space, Banach spaces E and the linear operators. These really occur in wide variety of physical systems. Moreover, I would like to state that in this work, 4 deep mathematical fields are related: theory of partial differential equation, a theory of operator, theory of interpolation of Banach space, and harmonic analysis, namely abstract harmonic analysis. Now, we consider what this equation, Schrödinger equation. Since what you see that what here A is we will say condition for A, but we will suppose that A is tutorial operator, and here this is convolution term A, and here define what does it mean, convolution operator and function, and where AX and the B equal BX are linear and the nonlinear operator function, but B is nonlinear operator function, but A is AX linear operator. You will see that this will dispositive operator. We will suppose condition that this operator generates analytic semigroup, and this such type operator directs the fractional power of such this operator. Here, we consider this question in Banach spaces, and what the function phi x is E-valued, that is Banach space valued function. We will say in what class, because of when we consider such equation with unbounded operator coefficient, you know that there is a trace problem. First of all, we must construct spaces, abstract spaces. You know that if A is, for example, constant, and the space E is a space of complex number, then we obtain scalar problem. That is classical Schrödinger problem. Here, main mechanism, that is the spaces that we need, is Sobolev spaces. But the Sobolev spaces studied, you know, by many mathematicians, that M-bending theorem, trace theorem, that need in theory of PDE, partial differential equation. But when we consider abstract equation, then that is we need some spatial class of function that we denoted it by Sobolev-Lyons spaces that I have the chance of a great relation, Sergei Sobolev and Jacques Lyons in Moscow. What the space that we construct, I called it Sobolev-Lyons spaces and Besov-Lyons spaces. What one of my people, Oleg Besov. I denoted what these spaces, Sobolev-Lyons spaces and Besov-Lyons spaces. What in this paper, the method of proof naturally differs from those used in previous work. Indeed, since the problem included an abstract operator, a leading part of the equation that considered in evaluate LP spaces, where P may be different too. That is here considered general non-Hilbert spaces. We need some extra mathematic tools for deriving considered conclusion. For this reason, in the proof, we use modern analysis tools like the following. First, operator valued multiplier theorem in abstract LP spaces, embedding and the trace theorem in Banach value sovereign Lyons spaces, theory of semi-group of linear operator in Banach spaces, perturbation theory of operator and interpolation of Banach spaces. Really, when we consider what this problem, one of main issue is to choose the class of function phi. Since phi x is evaluate function, but u in definition of u, we suppose that the function u belongs some Sobolev Lyons spaces. That is, this is abstract function. With that is the function is the A value, that is domain definition of A, derivative of this function, Sobolev Lyons, that belong to LP spaces. But the function is given from the more smooth spaces. We proved here the existence, uniqueness, and LP regularity properties to solution this equation. The LP regularity of this equation depends critically on the presence of a suitable kernel. What you see that you know that when considered Schrödinger equation, this part undergraduate, sometimes some mathematician, the operator Laplace, and maybe here we can put some degenerate operator, different, this part, that is elliptic operator. In all situation up to this time, these principal parts were self-adjoint operator. In this case, principal part is non-self-adjoint operator. Because of the method that we are dealing with, devoted directly to LP theory, the method of Banach spaces. We absolutely not use the nice properties of self-adjoint operator. But we know that the sectorial operator, if Banach space is Hilbert spaces, E is Hilbert spaces, and the A is self-adjoint positive operator, then really this operator also is sectorial. But the resolvent of this operator satisfies the minimal estimate, minimal growth condition. But here, since operator A is more general operator, we have different application. For example, instead of age, if we consider the instead of Banach space Hilbert spaces, then we can put here L2. If H is Banach spaces, we can put here, for example, sequence spaces, L2. And AB, we can take infinitely many matrices. Then we obtain infinitely many system of Schrödinger equation. But really you see that how much interesting the abstract setting in this case. So for the second application, for example, we can consider, for example, E some LP101, another Lebesgue spaces, and A to be degenerated differential operator in these spaces. Then really we can show that what this operator AX really is sectorial. This is also is very difficult questions to find to show that what this is a sectorial operator in this LP1. Then in result we obtain what such Schrödinger problem for the non-local Schrödinger equation with such for example non-local boundary condition. And we solve then the existent unit instance LP regularity for these mixed spaces. Namely, what in this case we obtain a Stricker type estimate because of, you see, P is mixed spaces, what LP is mixed spaces. Now what the definition of mixed spaces you know. Now what for the precise explanation or talk, I would like on some definition to remember you. What let E Banach spaces, what LPA sometimes denote both Nash spaces, the E-valued LP spaces with the norm. Here what we denote by let E1, E2 are two Banach spaces. Then what E1, E2 we denoted interpolation spaces, real interpolation. Maybe, but here we used real interpolation. Indeed, we, for example, can consider the problem for the when data what in the Schrödinger problem will be some interpolation spaces, I will show, for the complex interpolation spaces. But in this case, we can work with the real interpolation spaces. And what the operator, a closed linear operator is said to be phi dissipative in Banach spaces E, this bound M, if the dA and the range, the domain A and the range A are dense only, and kernel is 0, and the resolvent of this operator satisfies this condition. But here, since these operators have fractional powers, dissipative operator, we can the graphical norm. We can define graphical norm in this domain. Moreover, I will not explain the urban the concept of urban because of the space, the Banach spaces. The Banach spaces is called UMD spaces, unconditional martingale spaces. If Hilbert operator, this is one of nice theory of harmonic analysis. If Hilbert operator is bounded, you know that Hilbert operator or well-known Hilbert operator is what this Hilbert operator. You know that what Hilbert operator is on heart of the harmonic analysis. That really is bounded in LP spaces when P is between 1 infinity. What well known, this definition will initiated what American mathematics Burkholder and Bourget, Jean Bourget. They generalized this result in definition of UMD spaces, unconditional martingale spaces. That since these spaces appear in probability theory, sometimes it is given definition in terms of probability. But what a harmonic analysis version is that if the operator is a Banach space is called UMD space, if the Hilbert operator, what this Hilbert operator is defined on Schwarz spaces and is bounded in these spaces for that is a full generalization of scalar Hilbert theorem. Now, I think this is sufficient. Let me really, what's Fourier transformation? We here give what general convolution operator. If operator dependent on X we suppose that the domain of D are independent on X. This is one of condition, and AU some belong to the E-valued L1 spaces for U from the Schwarz, dA valued Schwarz spaces, and the convolution is defined what such. What here you will see that one of main method is method of harmonic analysis. What really all time I say that the PDE real analysis of PDE, the good result, it is in order to obtain good result in PDE, LPA, it is impossible without using of the harmonic analysis and the functional analysis and the theory of function, that is space, Sobolev spaces, and harmonic analysis. So specialists, what you see, PDE and harmonic analysis. Harmander, for example, one of world mathematics, Harmander, Jacques Lyons, now Calderon, American mathematics, Calderon, all these people's PDE and analysis, harmonic analysis, theory of function, and function analysis. This is impossible, another. Because of I proved it, but because of really when we consider what Allah now good now that when we consider abstract equation, first of all we have some preparation. Space, we consider space and the domain definition because of we consider unbounded operator in equation. Very serious steps should be to explanation of this problem. But here, we defined what these spaces in Soviet Union, what our definition when I worked in Soviet Union, what denoted as Sobolev-Lyons spaces. Because of really, I very liked Sergei Sobolev and Jacques Lyons. Jacques Lyons also with me, and we have some. I have a chance to meet Jacques Lyons also. What this space you see? What this is space of so-called Sobolev spaces, E-valued Sobolev spaces, but E-valued because of in 1950 year, Sergei Sobolev itself defined abstract Sobolev spaces. But there is really the first result, Jacques Lyons, that when Jacques Lyons considered optimal problem, there are some abstract problems. Equation with operator coefficient. So Jacques Lyons constructed spaces that the function sum itself from this E0 values, and the derivative from LP E value. Only here, suppose that E0 continuously and densely belong to space E. For example, if E0 is some domain definition of linear operator, for example, sectorial operator, it is well known that the E0 really is continuously and dense belong to E. So we defined what such spaces and called it Sobolev-Lyons spaces. Norm these spaces is defined. What I consider abstract differential equation, partial equation, abstract equation, I work in these Sobolev-Lyons spaces, and I have a lot of results with respect to embedding theorem, continuity and compactness of this space and the trace theory. Now really, I think this is sufficient. But here I give the Fourier analytic definition of base of spaces. Fourier analytic definition of base of spaces. What definition? First of all, with here the definition of spaces. The function who belong to these spaces. C1 to what here E infinite. What we have denoted as these spaces. This is the spaces of Sobolev-Yon spaces. That including this linear operator A, domain of operator. What you see that for main aim, we use our embedding theorem. That really what this is very important in theory of abstract differential equation. That's what does it mean? It does mean that what operator different. What this differential operator, mixed differential operator, is bounded from these spaces, Sobolev to this LQ, which you see what here interpolations, we obtain interpolation spaces. That is, then what this is very maximal theorem. It is impossible to generalize this result because of we find the best spaces that this differential operator is bounded from this Sobolev-Yon space to these spaces, and this is the Ehrlich-Nirenberg type estimate. Now, what really now we would consider really our problem. First, what we consider here linear and nonlinear Schrödinger equation. First of all, we consider this linear equation. What you said, this is independently have some interest on linear Schrödinger equation because of this is nonlocal equation because of have a convolution theorem, that's integral theorem, and the abstract function AX. And first of all, we consider the Cauchy problem for this equation. And what consider we will need because of it, interpolation spaces between these spaces we obtain that this is coincide what such type Sobolev-Yon spaces. You see that what this is interpolation between domain of A and E, 1pp interpolation spaces. Here, what if A is self-adjoint operator? Then what these spaces, the interpolation of coincide with the domain of A to power 1 to theta. If A self-adjoint, if I'm not self-adjoint, that so the case of self-adjoint for these spaces have been Jacques-Lyons, but the case of non-self-adjoint operator, it belongs us. We dealing with what first what the questions of embedding and different problem and for in Hilbert spaces and the Banach spaces. What you said of that what the well-known theorem of Jacques-Lyons and the Petre, they show that what trace operator you use is bounded from these Sobolev spaces to these spaces. Interpolation that is to the value of these interpolation spaces. What here you see we have the condition. In order to prove this result, really we consider here what in first we consider in this variable coefficient what A is complex valued function. A is but a small a, but a great A is operator function. What you see that we have this Grove's condition. What this Grove's condition appear due to the fact that we use Fourier multiplier theorem in LP spaces, Fourier multiplier theorem. What first first result I have. Our friend Hoca, how much minute I have? Minute 20.
15.
Yes.
Yeah,
All we showed that this linear problem under this condition has a solution. Then we what are conditions? Condition 2, assume that condition 2(1) satisfies, that is A is dissipative operator and some Grove's condition with respect to small a and great M, and what this is very good condition for the differential operator, and we suppose that S greater than Pn R P minus P 1 minus gamma minus 1. Gamma here, or you see why gamma, because of we will prove what this is, what this theorem, what this condition that is supposed with respect to S. Note that the condition 2(0) is T70 is on assumption on the parameters of P, parameter P, summability, n dimension of array. Gamma is what is the fractional powers of operator A, and S is the data spaces, the power of data spaces that we take. You see that then we obtain what this condition, P should be greater than SR minus N. In Schrödinger equation, you know that in case of L2, for local and global solvability, this is a condition necessary appear this condition with respect to restriction to summability of P. What theorem such that assume the condition 2 satisfies and the gamma is fractional number between 0 and 1. Let what data we belong is from the intersection of two spaces. First space is the Sobolev spaces A gamma value and L1 domain definition of the in this intersection. The function that Bilim function also from these spaces, the Sobolev spaces, fractional Sobolev spaces of S, but in framework of LP spaces all. Then linear problem 2(1) has a unique solution that belongs to, and the uniform estimator, uniform with respect to T. Moreover, if phi from what data is from these spaces, then the fractional powers and the convolution of UT differentiate of UT. This satisfies this. This is the proof is really based on I say a theory of partial differential equation and operator theory, interpretation of spaces, and multiplier theory. But I only will say some sentence about the really in order to prove this result, we must show that what these operator functions are multipliers from LPC space into infinity. What in this case we can instead of infinity, let we put LP. Why? because of in this, if we consider interpolation spaces, then we will LP. But if data spaces will from the normal Sobolev spaces, then we can consider this problem from LP to infinity. That is, P maybe from 1 and infinity. By using the multiplier theorem of Gerard and Weiss, then it is sufficient to show that what this operator function belong to these base of spaces, bounded operator valued base of spaces, bounded value. But now we use here embedding theorem. Really, you know that then what the relationship between Sobolev and the base of spaces, then it is sufficient to show that what this operator function belong to this bounded operator valued Sobolev spaces for gamma greater than n. What assumption, restriction to S and P because of what this operator function belong to these spaces, if what this condition that appear between P, R, N appear, and we really show that really what these operator function belong to these Sobolev spaces. I note that maybe we here can use, for example, Hermander multiplier theorem or Michel multiplier theorem. But here we use the Lutz-Weiss theorem and Gerard and Lutz-Weiss theorem, that more general theorem. Here, what really you see that then we obtain what the estimate. The second theorem here for linear equation, what in the second theorem, our assumption is changed, but we consider the following assumption Groth's condition with respect to principal part of this Schrödinger equation with complex valued function and operator valued function. You see what there is a relationship between what is coefficient small a and the Fourier transformation of operator function. That if we would have this condition, then we show that if the condition 2, 3 satisfied, then for phi from the Sobolev spaces E value and the data from the same spaces, there is a unique solution. That the following uniform estimate role. Here also we use the technique of operator values multiplier theorem, interpolation of space, and a fraction for of theorem. Now we will what this regularity theorem can be used to obtain local existence of corresponding nonlinear Schrödinger equation. For this case, for the proving, we will use and we have to generalize the good theorem of this outstanding growth mathematics, Nuremberg. You know Nuremberg inequality. Really, we can show that if, for example, in simple case, if H is Hilbert space, because of what this estimate, very important in nonlinear theory, Hilbert spaces, and assume that U is from this space, H valued LP spaces, derivative is H-valued LQ spaces for PQ from 1 infinity. Then for I between 0m and m greatest n2, we have the following estimate. In order to apply to have application of this theorem, since this theorem was only in scalar case, that is in case of H is complex number, we generalize this theorem Nuremberg. At the same time, we have to generalize again real now mathematics from Princeton University. Sergei Kleinerman, one of that rules world mathematics analysis and PDA. Sergei Kleinerman theorem. We generalize this theorem also for the abstract Hilbert spaces. Really, in what here, right? If H is complex number, then we obtained. Now, moreover, we generalize what you see. Some real result, that have been proved in scalar case. Some results, when this is really very simple, what you see, I write that by reasoning as what this theorem, one of theorem is Cauchy theorem, the commutator theorem in harmonic analysis. Now, by using this, Lem, really, we now we will use in order to consider the nonlinear problem for abstract equation. First of all, we must find a nice trace spaces, data where we have to take trace that the solution has a meaning, good meaning. We would consider what here interpolation spaces. We will take our data function from this interpolation of these spaces and use the Lyons-Petre result, trace theorem, and really we now can state one of theorem nonlinear Schrödinger equation. What you see that what here we give a assumption with respect to nonlinear operator bx. Bx is bounded operator function in H, bounded operator, whose Fourier transform satisfies this Gross condition. Then the condition tree, what you see now, the condition to nonlinear operator. The nonlinear operator such that this is measurable from x0 is interpolation spaces. x0 rnt time x0, what from this to H is measurable function for U from interpolation spaces. Moreover, what this function is continuous for U from this interpolation space. Moreover, but the extra condition, if as a function belong from the CS plus 1, S is the order of these Sobolev spaces, but from x0 to H as a function from x0, that is interpolation from interpolation spaces to uniform with respect x to Rn. Then let the theorem 3.1, I only will be explaining. Let the condition 3.1 holds, and the gamma is the between 0 and 1. Then there exists a constant delta such that what is this local self-additivity for small data. Uniqueness theorem we derived by using this small data, such that few from these spaces constructed with, and we suppose that norm is these spaces, small than this delta. Now, when we use existence theorem, we will use this delta with this delta. Then the problem, then this nonlinear problem has a unique local strong solution that belongs to these spaces. Satisfies what you see. This estimate, you see that the nonlinear estimate depends on this data, depend on data norm delta. What I on the scheme of this, I can show this. Of course, you know that when we consider nonlinear equation, we just using the fixed point argument. We consider the operator, nonlinear operator, that, and we show that really this operator is fixed, contractive operator. So from this general nice theorem, we obtain that the solution, there is a unique solution. But we here also have benefit that we from this theorem get that our solution is maximal regular. That is belong to the Sobolev-Lyon spaces. Now what we use this result fixed theorem technique, and again Therese theorem, and one of here important moment, we here use the regularity properties of corresponding linear operator. That's also linear. This is you know that all the nonlinear problem in order to what this is maximal regularity, what very interesting, because of it is gives an opportunity to consider nonlinear problem. If you have maximal regularity result, for example, in LP spaces or Hölder spaces, then it is it can be used to consider nonlinear problem. Without this theorem, it is impossible. It does not work. Technique of nonlinear analysis. So what we now we can another theorem for global solvability, and we consider in Hilbert spaces. And we have some theorem 3.1, 3.2, and 3.3 concerning the existence units of nonlinear problem under different sufficient conditions. Now, what we can consider conservation of energy and the global existence. Really, what you see, what here extra condition. Suppose the condition to satisfy, assume that the kernel B satisfies this more restrictive condition. Then what we have here some results really concerning what this convolution operator. What we denote what this operator and prove some interesting properties of this operator, and really we here some lem, different lem, and finally we show that then what inverse of the operator satisfies this condition, and what we consider the energetic spaces. What we consider this functional. But by using this functional, really then we show that for any T, the energy, what this energy is constant. You know that what this is gives a chance to solve the global solvability in L2. And now so we have some result, and finally we really we derived that the problem have a global solvability. Well, here application, about application I see. Many thanks for your attention. You see that the concept is very wide. So really, you know that the precise explanation, we need some time and energy. Many thanks. Allah